In this lecture, we're going to discuss the type of crystal structures that are found in ceramic materials. And then we will know how do the crystal structures of ceramic materials differ from those for metals. After this lecture, you should be able to do the following. First, sketch or describe unit cells for sodium chloride, cesium chloride, zinc blende crystal structures. And when you're given the chemical formula for a ceramic compound and the ionic radii of its components ions, you should be able to predict the crystal structure. Because ceramics are composed of at least two elements, and often more, their crystal structures are generally more complex than those for metals. The atomic bonding in these materials ranges from purely ionic to totally covalent. Many ceramics exhibit a combination of these two bonding types. And the degree of ionic character depends on the electron negativity of the atoms. So here are a couple of examples for the degree of ionic character in different materials. So in calcium fluoride, it has more ionic character than covalent character. But versus silicon carbide, it has smaller ionic character, which means it looks more like covalent. For those ceramic materials with predominantly ionic bonding, the crystal structures may be thought of as being composed of electrically charged ions instead of atoms. So here, let's do a quick review of the terminology. So if the ion is positive charged, then we call it cation. So cation have given up its valence electrons to the non-metallic ions. And another one is called anion. So anion are negatively charged ions, which means it receives valence electrons from the metallic ions. So we can simply say the ionic crystal structure can be viewed as close-packed structure of larger anions, since anions are negatively charged ions because it receives the valence electrons. Typically is larger, but it's not absolutely larger. Okay, so usually if it's larger, then this crystal structure can be viewed as close-packed structure of the larger anions with cations fit into appropriate interstitial sites. So the interstitial sites are the voices between the anions. For example, if we have the oxide structure, the oxygen anions usually are larger than metal cations. So we can view the oxide structure as close-packed oxygens in a lattice, and usually this close-packed oxygen forms FCC structure, face-centered cubic structure. And the cations, the metallic or the metal cations, are thought to be fit into the voids or interstitial sites among oxygen ions. Now let's review the crystal structure and its relation between the lattice point one more time. So the concept of a lattice is mathematical and does not mention atoms, ions, or molecules. For example, if you have a cubic or cube, we know it must have 8 corners and then there are 6 faces. So it's a pure mathematical concept. It doesn't have anything to do with materials or crystal structure. So in materials, we borrow this lattice concept and we add bases to the lattice to define the crystal structure. So in other words, crystal structure equals to the lattice plus bases. So a base is a group of one or more atoms associated with each lattice point. For example, if we have a metallic or if you have metal, for example, aluminum, it has FCC structure. So this is the 2D lattice point. For example, assume this is the front face of from one of the unit cells of the aluminum structure, FCC structure. So we know there will be 5 points, 4 corners, and 1 in the face center. And if each point, we can put 1 atom at each point. So lattice plus the base. Base is 1 atom associated with each point. We have the crystal structure of aluminum, which is FCC structure. But now for ionic ceramics, it has 2 different atoms. One is usually metallic, one is non-metallic. Now, the base is still the same, or the lattice is still the same. We can still have a FCC structure, face-centered cubic structure. But now, each lattice point can be seen of associated with 2 ions. Now, we should not say atoms anymore, 2 ions. So overall, this is still a FCC crystal structure, but each lattice point has a base of 2 ions. Now, let's see one example. If I ask you, what is the crystal structure of cesium chloride? What is your answer? Well, if you take a look at this given crystal structure, we see there is 1 atom or ion at each corner, and there's another, the chlorine ion is at the body center. Well, look like it's a BCC structure, body-centered cubic, isn't it? But don't forget, we're talking about the crystal structure is a composition of the lattice point and the bases. Now we have 2 types of ions. Each lattice points need to be seen as associated with 2 ions. We can divide this chlorine ion into 8 parts, and each part is associated with 1 corner. Or we can just use 1 type of ion, the cesium ion, and this cesium ion forms a simple cubic then we put this chlorine ion at the body center or into the voids, into the interstitial site of the cesium ions. So, in fact, the cesium chloride has a simple cubic structure, and with 2 ions associated with each lattice point, so we say this is a basis of 2. And cation forms the simple cube, with anion occupy the cubic interstitial sites, or the center of the cube. So what factors that will determine the crystal structure of ionic ceramic materials? Well, 2 characteristics of the component ions in crystalline ceramic materials influence the crystal structure. So the first one is the magnitude of the electrical charge on each of the component ions. And the second factor is the relative sizes of the cations and the anions. So for the first characteristic, the crystal must be electrically neutral. In other words, the net charge in ceramic should be 0. So all the cation positive charges must be balanced by an equal number of anion negative charges. So the chemical formula of a compound indicates the ratio of the cations to anions, or the composition that achieves that charge balance. So M and P are the number of cations and anions respectively, and those values should satisfy charge neutrality for this compound. For example, in calcium fluoride, each calcium ion has 2 positive charges, and each fluorine ion has a single negative charge. So there must be twice as many fluorine ions as calcium ions, and which is reflected in this chemical formula. Ca, one atom or one ion associated with two fluorine ions to achieve the charge neutrality. The second characteristic involves the size or ionic radii of the cations and anions, R sub C and R sub A respectively. So because of the metallic elements give up electrons when ionized, so cations ordinarily are smaller than anions. Therefore, this ratio Rc over Ra is usually less than 1. And each cation prefers to have as many nearest neighbor anions as possible. And also the anions also desire a maximum number of cation nearest neighbors. So the stable structure means maximize the number of oppositely charged ion neighbors. And also stable ceramic crystal structures form when those anions surrounding a cation are all in touch with that cation. For example, this is the unstable crystal structure because we have anions form closed packed structure and there is an interstitial site, looks like a diamond site, right? Or a void between those cations. We can form between those anions, and we can place one cation in this void or in the interstitial site. But since this one is too small, and this cation is too small, it's not in touch with the nearest neighbors, with those anions. So this is the unstable crystal structure. And this one is a stable structure because this cation is perfectly fit into this void. And it's in touch with all the neighboring anions. And this can also be a stable structure. So the radius of this cation is slightly bigger than the size of the hole or than the size of the interstitial size. So it pushes out the close-packed anions a little bit. So the anions are not in touch anymore. But since the cation is in touch with all the oppositely charged ion neighbors, so this is also a stable structure. In other words, the atoms or ions we put into the interstitial size or into the voids should be at least the same size or bigger than the size of the interstitial size. We cannot put a smaller cation into the interstitial site. That will form an unstable crystal structure. We have mentioned interstitial sites many times. So let's take a look at what are interstitial sites. So in any of the crystal structures, there are small voids between the usual atoms. Since atoms are hard spheres, there will be gaps or voids between the spheres when we pack them together. And into those voids, smaller atoms may be placed, and those locations are called interstitial sites. So the familiar or common interstitial sites including cubic site, which occurs in simple cubic structure. If we place 8 atoms together, stack them together to form a simple cubic, there is one void or one type of interstitial site between the 8 or in the middle of the cubic center, and this will be the cubic site. So cubic site has a coordination number of 8 because this blue atoms, which is the atom we're going to put inside the interstitial site, should be in touch with 8 atoms that form this interstitial site. So coordination number is 8 for cubic site. Another one is the octahedral sites, which can be found in FCC, BCC, and HCP structure. So this octahedral site is when we place 6 atoms together. So for example, we're going to stack 4 or put 4 atoms on the table first to form a square, and then we put 1 atom on top and put another atom on the bottom. So top there's 1, then put 1 directly under this top atom to the bottom. So we have 6 atoms packed together. And between the 6 atoms, there is a void. And this void is the octahedral sites. And the coordination number is 6 because now we have 6 atoms packed or stacked together, leaving that void in between them. The last one is the tetrahedral sites, which also can be found in FCC, BCC, and HCP structure. This is when we put 4 atoms together in touch, close packed, and there will be 1 void between those among the 3 or inside the 4 atoms. And this is the tetrahedral site. If we connect the center of all the 4 atoms, this will form a tetrahedron. And the coordination number for tetrahedral site is 4. So this atom we put in the middle in the void or interstitial site will be in touch with 4 other atoms. So the coordination number is 4. And in FCC structure, there are 2 types of interstitial sites. One is the tetrahedral and one is the octahedral. Well, for the tetrahedral, here is just to illustrate where is the tetrahedral interstitial site, so we can find the location of the cation. Right? When we have anion form the FCC structure, if we need to locate a cation inside the tetrahedral interstitial site, here is where it should go. So this tetrahedral interstitial site is formed by 1 corner atom. This is in the gray color, gray, and 3 adjacent face center atoms. And 4 atoms form or are close touched, close packed, and in the middle there is a void. So that's where another cation or another oppositely charged ion can be placed in. So that's the tetrahedral. The octahedral, which has a coordination number of 6, are formed by the 6 face center atoms, and the ion or oppositely charged ion, for example, cation, can be located in the middle of this tetrahedral interstitial site to form the ionic bonding. There is another octahedral site in FCC structure which is located at the edge center. So let's take a look. It has a coordination number of 6. It will be formed by 2 corner atoms, one in the this corner, front corner, and one to the back corner here, and 4 face center atoms. So this is 1 face center at the bottom face, and another face center is in another unit cell, adjacent unit cell to the right, and 1 face center atom on the right face center, and another face center is in, again, the unit cell below, also on the right face. So those are the 6 atoms which are in touch, and in the middle there we can place another cation inside to occupy this octahedral interstitial site. Here are the interstitial sites in BCC structure. One type is the tetrahedral, another one is the octahedral. For the tetrahedral, we can visualize it, which is formed by 2 body-centered atoms from the adjacent unit cells and 2 corner atoms. So the additional cation, for example, can be fitted inside this tetrahedron. The octahedral interstitial sites are formed by 4 corner atoms shared by the 2 unit cells and the 2 body-centered atoms from the adjacent unit cells. And the additional cation will be fitted into the middle of this octahedron. We presented earlier the 2 characteristics to define or to figure out the crystal structures of ceramic materials. One is electrical neutrality. The charge on the material should be 0. Use that condition or use that characteristic, we can find the number of anions and the number of cations in one unit cell, because each unit cell should also have a 0 charge. And the second characteristic is the ratio of the ionic radius, RC over RA. So when do we use it? Well, after we figure out the number of anions and number of cations, usually we say the anions will form a crystal structure. For example, if the anions form a FCC structure, then we need to locate the cations. We learned there are interstitial sites in the FCC structure, but there are 2 types of interstitial sites, and there are more sites than the number of cations. So where should we put the cation? Which kind of interstitial site, tetrahedral or octahedral? Well, the second characteristic, the RC over RA, can help us answer that question. So we mentioned the stable ceramic crystal structures form when the anions surrounding a cation are all in touch with that cation. And the coordination number, which is the number of anion nearest neighbors for a cation, is related to this cation-anion radius ratio. So the coordination number increases with RC over RA. And again, how do we find to form the stable structure how many anions can surround it around a cation, or in other words, which interstitial sites should we place the cation? Well, for a special RC-RA ratio, and there is a critical or minimum RC over RA ratio. For example, if RC over RA is less than 0.155, the associated coordination number is 2, which means we can only fit one cation between 2 anions, and which is the linear relation. Or if the RC over RA is between 0.155 and 0.225, the coordination number is 3, which means we can only place this cation inside the void formed by 3 anions. Well, again, the most commonly used coordination number, or most commonly found coordination number in crystal structures, will be 4, 6, and 8. So the coordination number is 4 when the RC over RA is between 0.225 and 0.414. So the cation is located at the center of tetrahedron, with anions at each of the 4 corners. And between 0.414 and 0.732, the cation may be thought of as being situated at the center of the octahedral, surrounded by 6 anions, so the coordination number is 6. And when RC over RA is larger, between 0.732 and 1, the coordination number is 8. That means we need to have 8 anions to form a void that is large enough to hold this cation, because the radii of the cation and anion in this category is very close. And the common materials that have coordination 4, 6, and 8 respectively are the zinc blende structure, which has the FCC structure formed by the sulfate ions, which are bigger, and with the zinc ions fitted into the center of tetrahedral, because their ratio, or the RC over RA ratio, is between this range. Coordination number must be 4, so that's the assembly of the zinc blende structure. And the next one with coordination of 6 is the rock salt structure, or the sodium chloride structure, with the chlorine ions form the FCC structure, and because the ratio of RC over RA is between this range, it has to be the sodium ion has to be in the center of octahedral, and this is the final crystal structure. It is FCC structure as well, so the zinc blende is also FCC structure. And with coordination number of 8, the cesium chloride has this kind of crystal structure, with the chlorine ion form the crystal structure, and the cesium ion is at the center of the cube. But again, this is not a BCC structure. It is the simple cubic structure. Let's take a look at one example, predicting the crystal structure of iron oxide. So on the basis of ionic radii, what crystal structure would you predict for iron oxide? And we're given the radius for some cations and radius for some anions. And in this example, in the iron oxide or ferrous oxide, we know this iron should have 2 positive charges, and the oxygen has 2 negative charges, so we can locate the ionic radii for them respectively. Since the ratio of the radii or ionic radii will determine what kind of crystal structure this material should have. So let's calculate the ratio of RC over RA. Again, that's the critical factor to determine the crystal structure of ceramic materials. And the result is 0.550. And based on the critical radii ratio or critical ratio for RC and RA, we know for this number, the coordination number must be 6. And the representative material for that is the rock salt. Again, coordination number should be 6, and the crystal structure is identical, or it's the same as the rock salt structure. But keep in mind, this is only true when we have XP type ceramic material, which means in the chemical compound, the ratio of the cation and anion is 1:1. And if this is true, then we can use those representative type of materials to represent the crystal structure. So again, for this one, the crystal structure is the same as the rock salt. Some of the common ceramic materials are those in which there are equal numbers of cations and anions. These are often referred to as AX compounds. So the subscript we saw earlier, the P and M subscripts are 1. So the ratio between the number of cations and anions is 1. So A denoted the cation and X is the anion. There are several different crystal structures for AX type compounds, and each is typically named after a common material, just like the example we did. First one is the rock salt structure or the sodium chloride structure, and the second one is the cesium chloride structure. And the last one is the zinc blende structure. Let's take a look at each of those three structures. The most common AX crystal structure is the sodium chloride or the rock salt structure. So the radius for the sodium cation is 0.102 nanometer and the radius of anion is 0.181 nanometer. So we can calculate the ratio of RC over RA, which is 0.564, and it is roughly between 0.414 and 0.732. And based on the table or based on the critical ratio, we can find the coordination number has to be 6, which means the cations prefer the octahedral sites. So therefore we can see the structure as the anion ions form FCC structure, and with the cations occupy the center of the octahedral sites. We can also get, from this FCC crystal structure, we can also get the number of ions and number of cations in the unit cell. For the anion, the chlorine anion, we have 8 corner atoms or ions and 6 face ions, a total number of 4 anions in one unit cell. And for the cation, which are at the edge of each unit cell, and we know each edge is shared by 4 unit cells, so 12 times a quarter, plus there is 1 in the body center, which just belongs to this specific unit cell. So the number of cation in one unit cell is also 4. So the ratio is 1:1 for the sodium chloride. And we can also get the lattice parameter. So the lattice parameter equals to the radius of, or actually the diameter of the anion plus the diameter of the cation, or the radius of the cation plus the radius of the anion equals to the half of the lattice parameter. Again, with this number, we can say there are 4 sodium chloride formula units per unit cell. So with the same characteristic, we can also figure out the magnesium oxide and iron oxide also have the rock salt structure. And based on the ratio of RC over RA, we have the ratio is 0.514. Therefore, the coordination number must be 6. So the cations prefer the octahedral sites. And again, this coordination number is true for both. So the coordination number for both cations and anions are 6. There are 6 cations surrounding each anion, and there are 6 anions surrounding each cation. Another common AX compound structure is the cesium chloride structure. So here you're looking at a unit cell for cesium chloride. And first, let's check the ionic radii. So the radius of the cesium ion is 0.170 nanometer, and the radius for chlorine ion is 0.181 nanometer. So the ratio of Rc over Ra, the radius of the anion over the radius of cation, is 0.939, is almost 1. So that means they're very close. The size of those ions are very close. Therefore, well, the cubic sites are preferred, which means the cesium cation will enter into the cubic sites, which is at the center of the cube formed by this chlorine ion. So the cesium chloride is a simple cubic structure with 2 ions associated with each lattice point. So again, this is not a body-centered cube, but a simple cube. And chlorine ion forms the simple cube arrangement, and cesium ion occupies the cubic interstitial sites. So the coordination number for both ions are 8. I should also mention that when we interchange the anions with cations, in other words, if we use cesium to form the simple cube and place the chlorine in the middle, we will have exactly the same crystal structure. So that's probably when you check some reference or some other resources, you'll see the opposite unit cell. But it's just a way of how you choose the unit cell to representing the entire lattice arrangements. It won't change the material itself. A third AX structure is one in which the coordination number is 4, which is the zinc blende structure. So the radius of the cation is 0.074 nanometer and radius of anion is 0.184 nanometer. We can then calculate the ratio of the cation over anion, which is 0.402. And checking the table for the critical radius ratio. With this ratio, the coordination number must be 4 to reach a stable structure. Therefore, the anion will form the FCC structure, and with certain number of cations fit into the interstitial sites, which will be tetrahedral interstitial sites. Well, since there are 8 tetrahedral sites, how many cations do we need? Well, to answer that question, we need to check the electrical neutrality. First of all, we know that we have zincs, not zinc, but the anions, the sulfur anions, which form this crystal structure, FCC structure, and we can calculate the number of anion in this unit cell, which equals to, we have 8 corner atoms and 1/8. Each ion belongs to 8 unit cells, and then there are 6 face ions, which is shared by 2 unit cells. So the total number of the anion is 4. So to reach the neutrality, electrical neutrality, the number of the cation also needs to be 4. So that's why we locate 4 zinc cations into the tetrahedral interstitial sites.